The classical planetary model of the atom is mathematically obsolete. Electrons do not follow fixed circular paths around a nucleus like planets orbiting a star. Instead, they exist as continuous matter waves, smeared out across three-dimensional space without a single defined physical location. In 1926, Austrian physicist Erwin Schrödinger sought a mathematical framework to describe these confined particle waves. He needed an equation that could do for quantum mechanics what Newton's second law did for classical mechanics, predict exactly how a physical system evolves over time. To understand modern physics and chemistry, we must abandon the comfort of classical certainty and embrace the mathematics of wave propagation. This is the time-dependent Schrödinger equation. It governs the behavior of all non-relativistic quantum systems. Our objective is to derive this exact formula from classical first principles and quantum relations. By building this equation step by step, we can see exactly how abstract mathematics generates the physical, three-dimensional shapes of atomic orbitals. This derivation will show that moving from classical particles to quantum probability is the logical result of how matter behaves at the smallest scales. We begin with a free particle moving through a vacuum, completely unaffected by external forces or potential energy. We describe this particle as a complex plane wave, with real and imaginary parts oscillating as it travels. The equation is psi equals an amplitude times e to the I times kx minus omega t. By de Broglie's relation, wave number k is proportional to physical momentum. By the Planck-Einstein relation, angular frequency omega corresponds to total energy. We substitute these physical variables into the exponent. The particle's classical physical properties, its momentum and energy, are now encoded directly within the phase and frequency of this abstract wave function. Curious, analytical tone. How do we extract the exact values for momentum and energy back out of this complex wave equation? Taking the spatial partial derivative of the wave function with respect to position pulls the momentum term down from the exponent. Rearranging the constants isolates the exact momentum. We repeat the process for time. The partial derivative with respect to time pulls down the energy term, isolating the particle's total energy. This reveals the core mechanics of quantum theory. Classical variables for momentum and energy are replaced by these specific differential operators. In quantum mechanics, observable physical quantities are no longer static numbers. They are active mathematical operations performed on a wave state. Now we return to classical mechanics. Total energy equals kinetic energy, momentum squared over 2 times the mass, plus potential energy, V. We substitute our newly derived quantum differential operators for E and P into this equation. Applying this yields the full time-dependent Schrödinger equation. By grouping the kinetic and potential energy operators together, we define the Hamiltonian operator, which represents the total energy of the system. If the potential energy does not change with time, we can separate the variables to form the concise, time-independent Schrödinger equation, h hat psi equals E psi. We have successfully translated the classical conservation of energy into the fundamental differential equation governing the quantum realm. But what is this wave function actually describing? A complex-valued amplitude filled with imaginary numbers has no direct physical equivalent in the real world. In 1926, physicist Max Born proposed a solution for interpreting these abstract waves. Born realized that multiplying the wave function by its complex conjugate, taking the squared modulus, eliminates imaginary numbers, generating a positive probability density. This graph dictates the exact likelihood of finding an electron at a specific point when you make a measurement. The Born rule mathematically proves the end of deterministic trajectories. At the atomic scale, we can no longer predict where a particle is, only the statistical chance of it appearing there. We can now apply this time-independent equation to a real physical system, an electron trapped in the electrostatic potential well of a proton, forming a hydrogen atom. Solving a differential equation for a confined particle requires strict boundary conditions. The wave function must smoothly approach zero at a distance from the nucleus. Confinement restricts the electron to discrete resonant frequencies, like standing waves on a guitar string, projected into 3D spherical coordinates. These standing waves generate the recognizable probability clouds called S, P, and D orbitals. The defining quantum embers emerge naturally from solving this equation. The Schrödinger equation replaced the outdated image of solid orbiting particles with a universe of probabilistic wave functions, providing the rigid mathematical foundation for every chemical bond and physical interaction we observe today.